I need permission to share.
Jerry, give.
Yes,
which one is your...
I want to share with Atel. Let me test. Okay, good. Let me see if I can share. Okay, so let me try to find the right slides to share. Can you see it?
Yes.
You can see the slides? Okay, good.
Okay. I think let's start. Okay. Good morning, everyone, and good night, everyone. And it's my great pleasure to introduce today's speaker, Professor Jim Dai from the Cornell University and the Chinese University of Hong Kong at Shenzhen. And today's talk is about scalable deep reinforced learning for ride-hailing. And I first need to introduce Professor Dai. And Professor Dai is the Leo C. Welch Professor of Engineering in the School of Operations Research and Information Engineering at the Cornell University. He is also the Dean of the School of Data Science at the Chinese University of Hong Kong at Shenzhen. From the 1990 to 2012, he was on the faculty of the Georgia Institute of Technology. And Professor Dai also received his bachelor and master in the mathematics from Nanjing University and his Ph.D. in mathematics from Stanford University. His research areas in applied probability focus on the stochastic processing networks and regional reinforced learning. His research awards include Erlang Prize and ACM SIGMETRICS Achievement Award. He served as editor-in-chief for the Mathematics of Operation Research from 2012 to 2019. Welcome, Professor Dai. It's your turn.
Thank you. Thank you for the introduction. And most importantly, thanks Professor Zhu and Dr. Qin for the invitation to speak in this seminar series. I note that the name of this seminar series, Applied Reinforced Learning. And I think that the keyword applied is very fitting. And I think there's a lot the community can do to make reinforced learning is a powerful tool to make impact in many applications, particularly for operations, service operations. So today, I'm going to share the work with my group members on this line of work for ride-hailing platforms. So these two collaborators, Aurora Feng, she was a former student, PhD student at Cornell, and Mark Grossman is a current PhD student. Actually, he's graduating. We have been working on this reinforced learning, this area for a number of years. And so Mark is graduating, and he currently looking for open to search for a job in the industrial lab. So in 2017, that was my first trip to Uber. 2017, early 2017. I remember vividly, talked to a number of people, colleagues there. One thing really struck me is a message from Uber saying that you don't have to own a car, right? As a picker person, citizen, you don't have to own a car. I thought that time was this very visionary goal, okay? Well, it's also very high order. It's very difficult, maybe very difficult to achieve, to convince the public, citizens that you have to give up owning a car. Now, if you're thinking about it as an average citizen, for me, for example, in order for me to to make that decision not on a car, I need to have the confidence that these ride-hailing services are very reliable. Reliable keyword. So today, for example, this morning it's raining, and I need to send my boy to school. I'm able to get the car, right? So that trip really focused my attention on this matching rate. So how can a platform can provide good quality service, okay? It's not just revenue, right? Revenue is 1 year, can up and down. But long term, to build that trust, you have to provide reliable service, okay? Otherwise, that vision cannot be achieved, okay? So this work is on matching and repositioning. Now, very timely, there's a very nice survey paper that appeared just a few weeks ago, okay? And by this group of experts, and two of them here on this right now on the Zoom. And so they are the experts, and they worked at DD, and they accumulated lots of experiences. And so this survey paper talk about a number of topics, okay? Ride sharing, matching, vehicle repositioning. By repositioning, I mean here, a driver currently at a location has no passenger, but the driver decides to move to another location, driving empty without passenger. That's repositioning, okay? Ride pooling, that's obvious, and I'm not going to talk about it here today. Routing meaning turn by turn, moving the car from one location to another location. And the dynamic pricing, you probably heard a lot about it. That's often also called surge pricing. This last point, let me make a few points. Surge pricing. We heard a lot about it, and why a platform implement that. Often is to deal with the imbalance between supply, which is drivers, and demand passengers. Sometimes the too many passengers in a location. So the dynamic pricing can do is that do the pricing. Suppose you have demand too much, your price goes higher, and a certain fraction passenger decides it's too expensive, I'll go away, right? That's maybe it's a good way to select these urgent passengers. These passengers value the service highly. Provide service for them. Maybe that's good, achieve good society benefit, okay? But dynamic pricing also being talked about something where maybe draw the supplier, more driver to that location. And I have, my view is that effect of that is limited, and maybe even negative, okay? The main thing is the timing, okay? So when you do the dynamic pricing at the location, the drivers are not there yet. And it takes time for them to get there, okay? But their demand situation, by the drivers get there, the demand situation may change, okay? Now, the only way to achieve that is maybe the driver can know that information, pre-positioning, go to that location. Now, this way encourage all kinds of problems. The drivers are strategic, right? So that's where creating all kind of gaming going on. And we heard some discussion along this line. So, okay, to solve this temporary imbalancing between supply and driver, supply and demands, I think repositioning is a much more effective way to do that. And repositioning is you proactively send driver to certain location in anticipation the future demand in certain area. But I understand this area is the repositioning has not been implemented, at least from my knowledge, implementing any platform. So, but this work is promoting this this line. Okay, so my work here, this line is to focus on first two bullet point here, matching and repositioning. Now, first of all, it's not too difficult to convince yourself that this is a difficult problem. Okay, if you have, say, just one region, one city, one region, you have M cars, okay, M drivers. M can be hundreds, and you have also hundreds of passengers. If you really want to be picky to find so-called Z-optimal drive matching at this time, there are many possible matches, right? So this number can get very high, and so this is just one possibility at this instant at decision time. So this matching problem is difficult. Okay, now which weight to use? That's also an issue. It's a more on each age to match. That's even more issue. Now this one here, we have seen papers along this line. This one is completely ignored the position. Okay, if you're adding the positioning, that's the things that position is much more complicated. So so today I'm going to talk about here is this paper here published earlier this year. Okay, now we achieve scalability. Okay, scalability of our algorithm through the I think 3 major factors. Okay, the first is efficient state representation. Okay, and the second thing is the hierarchical decision making. The third thing, the atomic action. I quote here, we use this term atomic actions in the PPO reinforcement learning algorithm. So the next half of the talk, before getting to PPO algorithm, I'm going to explain these 3 factors, okay, in detail. Okay, and so I think take away something that if you somehow later we decide when I get into the algorithm part, it's very detailed. You may want to remember this. These are 3 factors, okay, that we I think contribute to the scalability of our algorithm. Okay, efficient state representation, hierarchy decision making, and atomic actions. Okay. Oh, by the way, for this on Zoom, if you have something want to interrupt me to get clarification, please feel free to do so. I think that yes, I'd be entertained. That I think if you send me a chat message or something that I'm monitoring that. If there's a chat, I probably will look into that also. All right. So let me pause for a second to see in case some of you have a quick clarification questions. All right, so let me now describe, start getting into this, our model framework and our algorithm, okay? So in our model framework, we assume passengers willing to wait 8 minutes. Now, passenger wait, there are 2 kinds of waiting. Here, willing to wait, meaning waiting for a driver to show up. So maybe waiting for 5 minutes or willing to wait for 10 minutes, okay? So there another kind of wait, the passenger waiting for the assignment, right? Assignment driver, that's different. Okay, here do not explicitly model the waiting for assignment. Okay, that's maybe that time is a passenger window is waiting for assignment in 30 seconds. Okay, what if the passenger is not assigned a driver in 30 seconds? Well, the passenger will go away, but we can easily extend this thing so that the passenger willing to wait for a few decision cycles before the assignment. Okay, before the assignment, that's fine. So to make things less confusing, there's only one kind of wait here. So the wait for driver to show up. Now this AR doesn't have to be homogeneous. Okay, the passenger does not need to be homogeneous. But I pick one AR is for all passengers. It's just easy for me to do the presentation. Okay, so I just want to focus on the essence of things, but this non-homogeneity of passenger, that's not the major asset difficulty for us. Okay. Now, an important concept is available cars, available drivers. Okay. Now, availability often depending on the region. Okay, that's a region which I'm going to shortly introduce on the next slides. And this is it's important available in terms of what? Final destination. So suppose my final destination is B. Okay, the driver currently driving towards A, dropping customer a passenger in A, then eventually go to B. As long as this driver can get to B, destination B in 8 minutes, to me, that these drivers are available to be used in destination B. Okay, so that's availability. That's an important concept. So we currently using the drivers 2 hops away from the destination. We classify to be available. But if a platform to be more ambitious, they could just extend to say 3 hops. Okay, but I don't think that's a major factor. Okay, so we just say 1 hop meaning that the driver immediately drive into that destination. 2 hops meaning the driver need to go to the final destination, but before that they have to drop a passenger in another destination. Okay, so the 2 hops. Obviously, the third bullet point, we assume that the driver repositioning is allowed. Okay, so that's and the purpose is to address, as said earlier, to address spatial imbalance between drivers and supply and passengers throughout the day. Okay, now the last point is interesting. Deserve a few minutes, some discussion. So we currently assume that the centralized control, the platform has control. Drivers and passengers accept assigned trips. Now we know that's not true, right? That's not true. Now, particularly for the driver side, and particularly related to maybe reposition. Okay. Here are 2 things, several things discussion. First of all, they are in the future, right? One of these days, maybe this a driverless car will be into fleet, right? Certainly that will be relevant. In these cars certainly will can be completely controlled by the platform. The second thing that our algorithm can easily accommodate the situation when you have some hyperparameters, like say 20% drivers will accept assignment, right? 20%, that's hyperparameter. So if the model can accept the situation that certain fraction driver can refuse this assignment. I'm going to have a bit more discussion towards the end on this front. Okay. So let me now get into the 3 factors that I think that the 3 key factors that drive the efficiency, scalability of our algorithm or framework. So the first thing is the state representation. For state representation, the first thing we do is we have this concept of regions. Okay, so we divide a city into R region, capital R regions. Now, I have to remain a bit vague here that somehow this can be done. All right, this can be done, and I understand one way or another, each platform now, whether it's Uber, Lyft, or Didi, has some way to do this at multiple resolution level. Okay, so I assume this can be done. Now, important factor here is a region should be large or small enough so that the positioning cost of time within a region is negligible. That's really the driving factor. Now, again, negligible is depending on region. Like Ithaca, where the Cornell is, I think the entire time people are more, because we have few cars, the less density, and people are just accept the fact that they have to wait longer. So in that case, right, depending on air. So that's the capital air. So the accept longer. In that case, maybe one region is enough. Okay. All right. So that's region. Okay. The next part is state representation. Okay. So here on this slide, a region here, there's D here, often it's a destination, and O is the origin. Okay, so the first bullet point is to keep track of car information, driver information at region D. Okay, driver information. So important for region. So let me actually, this is important here. So let me mark here. So if you are currently for a region D here, I need to look at all the car status. Now, which cars? well, car maybe currently at region, currently maybe at another location, or maybe 1 hop away, I said earlier, or 2 hops away. These are, as long as they're available, these cars should be counted here, okay, counted here. And this number denote that the number of cars 8 minutes away, ADA is the parameter here, the 8 minutes away from location D. So maybe ADA could be 1 minute away, 2 minutes away, 3 minutes away from this location D. Okay, so I need to keep track, separate available cars into buckets. Some one bucket is 1 minute away, another bucket is 2 minutes away, another minute is 3 minutes away, etc. This need to be keep track for every region. Okay, every region. But important thing is I do not need to keep track of the GPS location or every car. I just need to be in this bucket, how many cars there, okay? So that's my information here, car information. Similarly for passengers, for each OD pair, origin destination pair, I need to see how many passengers are waiting to see here indicate cars, okay, cars, okay. So of course, I also need to keep current time, okay, in the state, okay, the current time. So again, let me emphasize from this model, our decision model point of view, okay, decision model point of view, I don't need to keep track of GPS location of every car. I do not need to keep track of passenger information, GPS location of every passenger, no need, okay? I just need to be, say, within each bucket, how many cars there, within each bucket, how many passengers there, all right? Okay. How can I turn off this caption here? Okay, good. If something can turn off caption? No, that's okay. Yeah. So the next factor contribute to scalability is atomic actions. So let me just now get into that. This is again important concept. Okay, so our policy, okay, to facilitate the region, okay, within the city, we're going to, so remember we have R square trip types, okay? Each OD pair represents one type, origin destination pair, okay? So our policy is to do the following. At each state, the policy will produce action, okay? Produce action, okay? Indeed, the policy will produce the probability vector. The probability vectors are this R square trip type. So each action is drawing from this probability distribution. That gives you a potential trip OD pair, okay, origin destination pair. So the total number of actions is R square, okay? So our reinforced learning algorithm is going to be mainly is to determine this pi, okay? So policy for each state S, what probability vector you can produce to choose these OD pairs, okay? So I will talk more about this, of course. Let's give you a preview of that. So the policy, let me quickly flash out here. The policy again to produce for each state, which is on the for each state. Okay, for each state. Remember that state is the driver information in each region, each bucket, and passenger information in each OD pair, And also the last part is the time, okay, initial time. And we're going to output the probability vectors, okay, a vector of probabilities, okay, vector of probabilities tells you which, this probability tells you how likely that each trip type is picked, okay. So that's the policy representation here. And it's so we have two hidden layers in our experiment. So that's feed-forward network. So I'm not going to say more about this neural network structures. Okay, so just give you idea that how we represent policy. Okay. So now explain atomic action here. This slide here. I hope this term used quite a lot, and this I hope you can pay attention to these slides. Okay. So we have each decision epoch. This is time epoch. Okay, this is real time. This is actually wall clock time. Okay, wall clock time. So for example, 9:01. Okay, that's decision epoch. That's for platform to inform drivers and passengers, etc. So the next time epoch will be 9:02 maybe. Okay, that I use this as example. Okay, so using 1 minute as a this is 9:01 at this time. From our algorithm point of view, multiple decision steps are performed, okay? Performed. So there are multiple decision steps. How many decision steps? Well, depending how many available cars at the time, okay? So if 9:01, there are maybe 1,000 available cars at that time, then I need to go through this decision steps 1,000 times, okay? But they all happens at 9:01. Well, but I want to do sequentially, okay, within my algorithm, okay? So the term, we use this term atomic action really meaning this, okay? Meaning that at 9:01, multiple decision steps are executed sequentially, okay? Each execution is taking action. This action is called atomic action from algorithm point of view. But when you inform this decision to the public, to your CEO, to the passenger drivers, you can wait, just announce at the same time. And that sounds like a batch decision, okay? So, but we solve this batch decision basically sequentially, okay? So, so that is, I hope the terminology is clear here. So now let me here get into more detail about this decision-making process. So here, I hope it's clear. This is a decision step, okay, decision step, okay. Remember at each time epoch, real time, wall clock time, we multiple decision epochs needed, multiple decision steps needed, and now look at one decision step at a time, okay. One decision, so currently we have in state S, we observe car location, car status, and also the passenger information, okay. If no available car in the entire system, this city, no available car, this car somehow in the middle of nowhere, right? From airport, maybe to long, far away downtown or something, all the cars just not available, okay, now. Then just you do nothing here. Wait for the next decision time, decision epoch. So wait for 9:02. Okay, you currently 9:01 a.m. You wait for the next minute. Okay, so you don't need to do anything. So all the cars in middle of nowhere. Okay. Okay, suppose that's another case. So there is a car, okay, in the system, available car in the system. This time I'm going to use the policy. The observer they're using policy to produce the policy, the neural network produce vector for me. Okay. So vector this time maybe if R equal to 10 regions, then the R square is equal to 100. So this vector is 100 dimension and tell me the probability of each OD pair is picked. Okay. So once I have known this probability, I can sample the OD pair. Okay. Origin destination pair. And so I sample that. If region O has no available car, then it's a useless sample. So I go to the slow way and then they sample another action, okay? Until this origin LO has available car. Now, I use this way to explain, just easier for me to explain it, okay? I think in practice, I just wait. This do the renormalization of this probability vector so that this will not happen. This once you pick an action, that action will have available car, okay? So that's that. Now, this region O origin has a car, available car, but very often, likely, you have a multiple available cars, okay? So which car do you pick? Which driver you pick? And this algorithm says, didn't say anything about that. So any such driver is okay. Okay, now you may think, wait a minute, I maybe want to do optimization, right? Something, this cannot be a good thing to do, right? How come you can allow any driver to do that? Well, this is something that is worth discussing, and I think some may consider this a drawback, and I really consider a feature, okay? So at this point, platform can do next level optimization, which is not in this model. For example, you can assign, suppose you have multiple available cars, you can assign the car maybe closest to the destination. OD pair, right, destination. Or you can assign a driver that didn't get many assignment yesterday, right? So you want to give this driver some fairness treatment, okay? Or you can assign driver to make, this driver is easy to get there to destination. Maybe this guy, it's just need to go to make right turns instead of left turns, particularly maybe in a city, congested city in San Francisco or New York City, this maybe it's more relevant, okay? Or you can assign the car according to the driver according to the revenue expectation, revenue earning expectation. Indeed, that's something that that's one area, how to retain drivers in long term. That's the survey paper that I mentioned earlier, that important question was not addressed in that paper. And actually, we have Costas Maglaris at Columbia, and we supervise a postdoc and exactly looking into that situation. How do you motivate a driver to stay in platform longer? So again, right? I'm here. Which driver to pick? This algorithm didn't tell you that. That's the next level optimization. We allow this framework, the platform can do next level optimization to pick driver. All right, so the driver is picked, okay? Now, which passenger? Well, if there is, so remember the reinforcement learning, the action, remember the action already tells you OD trip type, right? OD trip type. And now you also have a driver assigned from the origin. Now, if there is we going for this OD trip, okay? And if there is a passenger go from origin, from this location O and going to that destination D, then you pick any passenger, okay? Again, now the passenger, which passenger, if multiple passenger go to destination D, right? The algorithm again didn't tell you which one to pick. Anyone will work. Again, here the platform can do the next level optimization, right? So you want to reward this frequent, like airline have frequent flyer, right? So you can reward that. Actually, I had a personal experience with this in Shenzhen, China, that I actually sometimes I find it difficult for me to get DD car, whereas my assistant can easily get it. And assuming in that case that the platform there is aware that she orders cars very frequently, so she got a high priority. So again, which passenger? I consider this again a feature that the platform can do next level optimization, which is not addressed in our frame at this point in our algorithm. So if suppose there's no passenger, okay, go to OD. Now it depends on this D. If D is equal to O, okay, So in this case, the car has been signed, okay, picked, but no passenger there, and destination is the same as the origin. In this case, this driver should stay put, stay there, okay, don't do nothing. And maybe the platform should send a message to the driver, say, you do nothing and you stay here, and do not anxiously try to go elsewhere, right? I mean, currently, I think the platform probably do not suggest anything, but this, code, the lip positioning is proactively being implemented, then that maybe it's useful messaging to reduce the anxiousness of drivers. Okay, so this case do nothing here. Suppose that the destination is different from current location, okay, and you have assigned car and find no passenger go from on this trip, okay, go to that destination. In this case, send the car there empty. This is really we address lip positioning. Okay, so this lip positioning happening here. So at this point, lip positioning. So the car is at location O, and you pick this car and go on this trip, and there's no passenger available to go from destination D from this location. So in this case, you send the car to the destination empty. Okay, I hope that's clear here, the decision make process. Okay. Are there any questions, clarification needed? All right, so it looks like that's clear. Okay, that's good. So now my focus is to focus on how to define the policy. Remember, my focus is here, right? How do you get this policy here at each state? How do you give me the probability vector? Okay, tell me the likelihood of a particular trip type OD pair is being picked. Okay, so that's the focus. For that, we adopt the PPO optimization framework. That's in reinforcement learning. So it's not Q-learning or other policy gradient method. So by the way, this is a policy gradient. Okay, so it's a policy gradient method. We directly model the policy, right? Optimize over policy instead of the so-called value function based policy optimization framework, which I think toward the end I'm going to mention, but briefly talk about some literature. Okay, so this is a policy-based reinforcement learning algorithm. So what's the objective, right? When you talk about optimization, you need an objective. So the value function objective has this so-called one-step reward. Okay, one-step reward. Okay, you make one decision and currently at state S, and remember S is information about how many drivers in each bucket, and the passengers in each bucket. Okay, and this is action, taking action. So that's you immediately get some reward. Okay, now that could be revenue, etc. Right? So if to keep discussion simple, think of this as just F equal to 1 if you assign a trip. Okay, if you have one match, that's fine. Okay, so the customer passengers, right? If you just focus matching rate, that's 1. But it's easily you can accommodate here. This lip positioning G's can be the cost, lip positioning, right? Driving empathy. So you can maybe platform need to provide some incentive for driver to go there, so there's a cost. Okay, so you can easily incorporate this cost here. So the detail, this is not important, but easy way for you to think about that is F equal to 1, G equal to 0. In that case, corresponding to the really corresponding performance measure is matching rate, okay? So the V, what's the V? V is so-called value function. V is under current policy. Pi theta is current policy. So I have a current matching policy. And if I'm able to use current policy on many days, I probably can get the total reward on each day, and then averaging over many days, that's give me this one here, right? This S here, remember, this is starting point. Starting point, maybe if you're thinking of a starting point, the starting point is maybe 4 a.m. in a day, which means everything empty, no driver on the, approximately no driver in the system and no passengers, right? So the 4 a.m., that's the initial state here, okay? And H is a time horizon, how many decisions within a day you can make. Now that's depending on the batch decision time interval. So if it's 1 minute, then you just move each time 1 minute, T is 1 minute as a unit. Could be 30 seconds as a minute interval, or could be 10 seconds as an interval. Doesn't matter, okay? So you just, the platform can do that. Actually, maybe throughout the day can be, this doesn't have to be uniform, okay? It's not, maybe during rush hour, you want to be a bit, I'm not sure, but the decision epoch is a longer, smaller, doesn't matter. Just actually, what you need is that each day is consistent, okay? Each day is consistent. So each day to me is an episode. Each day is an episode, okay? So this is a finite horizon MDP, Markov decision process formulation. All right. So for those of you who are very familiar with a PPO algorithm, I apologize that here, but for those of you not intimately familiar with PPO algorithm, let me just provide motivation here, at least in this finite horizon setting, because in the original PPO algorithm that by Schumann and his co-authors, that was done by infinite horizon discounted set. Okay, so this is the final horizon. So the starting point is a motivated PPO algorithm is currently you have current policy pi 1. Okay, I want to find a new policy pi 2. And I want pi 2 to be improvement over my existing policy, of current policy. I want pi 2 is improvement over current policy. Okay, so that's the value or reward, or the reward, the expected reward if using current policy pi 1, and this is the reward for new policy. So you want this to be positive, this difference to be positive, right? Positive. And this is a sort of a standard, like often in the homework exercise, that has this expression. Okay, that it was the difference is given by this. Okay. So what's A? A is a so-called advanced function. Advanced function under current policy A1, pi 1, current policy. So advanced function is you currently in state S. And what's the advantage taking action A here? Well, advantage compared to what? Compared to otherwise you're taking action given by pi 1. So suppose if you want to take this action A, deviating from the previous action governed by pi 1. Well, this A is a measure that the advantage or disadvantage compared with taking action governed by pi 1. Okay, so that's an advantage function. Okay, so this right-hand side is going to be, okay, suppose my action is given by my new policy pi 2 to take according to pi 2, then I want to accumulate all the advantages by taking actions from pi 2, and that's the difference of the two policy, the reward of two policies. So that's sort of intuitive, right? So this is the advantage of taking pi A, taking action A to follow the current new policy pi 2, and accumulate all this advantage, that's the difference of the reward between total reward between two policies. Now, the problem here is that pi2 is yet to be found, okay, yet to be found. And yet to be found. And this one here, inside here, this can be computed, no problem. With the pi1, I can compute this one. I can get handle on this one. But this object value, take its value in terms of the new policy, which is yet to be discovered, that's going to be difficult, impossible to compute, okay? So this inequality here is something, replace this one, pi2 by pi1, that's all we did. And then we did a renormalization here, okay? So did the same thing. So this is just the input, change this pi to this thing here. So this ratio is changed. So that this expression here, the only thing new related to the new policy, yet to be found policy pi2 is in terms of this ratio. Everything else is in our hand. That's according to current policy pi1. All right, but there's a cost. The cost is that there's a different minus this one here. Okay, the distance between pi1, some distance, I use a distance not precisely, try to measure distance between pi1, pi2 here. So let me again try to explain what's going on. Pi1 is current policy. I want the pi2 is an improvement, a new policy. And I want this difference here to be positive. So this inequality allows me to say maximize the first term. If this term is positive, I have hope to have the left side to be positive, which means the policy pi2 is an improvement. But unfortunately, I have also need to take away this part, distance. So this suggests that maybe what we should do is to maximize the first term or keep distance to be small, right? That was original, all this line for PPO type algorithm was motivated by this. This was original in discounted in the discount setting, okay? So excuse me for 1 second, I need a very, very short break, okay? So a short break, just a second.
Yes, yeah, will be later.
Is that do I have Tony? Do I have a few more minutes, like 5-10 minutes?
Yeah, you have at least 10 minutes.
Okay, good. Thank you. Appreciate that. Let me continue. Sorry about that. Okay. So so this is what we call performance bounds. Okay, performance bounds, and so allow us to try to maximize this first term on the right side. Okay, while keep the distance small, right? That's this one. This seems the right thing to do. If you can achieve that, then you have a guaranteed improvement. New policy is a guaranteed improvement. Okay, guaranteed improvement. So that's the idea of the PPO algorithm. Okay. So I am so again, this is repeating same thing here. Okay, so this is the right, the first paper addressing, I mean, this whole idea about this performance band, it's really started with the Kakadi, Shem Kakadi at the University of Washington, and also Stanford. I think they are the first paper that introduced this so-called conservative update concept. But this is greatly generalized, introduced in 2 papers by Schumann is the first author on both these 2 papers. And the idea is basically we want to maximize this term, make it negative, positive, right? Maximize this term, find a new policy pi theta, so that this term is positive, and keep the distance to be small, right? So if you can do that, the new policy pi 1 or new policy pi theta is going to guarantee to be improvement of policy. Now, this is constraint optimization problem, right? Of constraint optimization problem, and then constraint is often more difficult. So in Schumann's second paper, suggests this using PPOs. This is it's using clipped surrogate object function. So here epsilon is a hyperparameter here, so that you want the ratio. Okay, the ratio you want to be around 1. Don't change it too much, right? I need a policy that don't deviate with my current policy too much. Okay, so this epsilon, the clip size is control that. Make sure the new policy is not deviate too much. And if you think about that, actually in real world application, a service system, that's actually making sense, right? So you want something that you don't want to drastically change current policy, because that's make your manager, anybody in that situation will be unnerving. Okay, so you want to change your policy gradually, smaller or gradually. So that's that. Okay. Now that's in terms of expect value under the current policy, right? But we can certainly using the data from current policy and do empirical formula, empirical object value, right? So that is the next slide. We're talking about that. So in order to form this object value, we need data, okay? So data is we need data for example, data from K episodes, or K days, okay, K episodes, okay, K days, okay. So each day is an episode. Now each day have multiple decision epochs, right? Each minute, for example, decision. So this may be the first decision epoch, first minute. This is the second minute. Within each minute, I have multiple decision steps. I need to keep track of state at each decision steps. Okay, multiple decision steps. And this is in the next minute, this minute decision steps. So this is on day K, you have time epoch T, you also have a multiple decision steps. You need to record its state information. Remember, again, state is not GPS location, etc. It's a harmony, the number in each bucket, okay? That's state. So from this data, you can easily formulate the empirical version of the object value, okay? And what's this empirical version of this one here? And this one here, the only thing that if you assume that assume this advantage function already known for the current policy given, here is you just the only decision variable here is in this policy network pi theta, and this one here in our case we just invoke standard optimization algorithm or implementation in the TensorFlow or within the PyTorch. We use Adam. Okay, Adam use default parameters work well. Okay, not much tuning at all for parameters. That's very encouraging. All right, so for that, I assumed that we assumed that already this advantage function already known. But in reality, we also not know. We also need to estimate that. Well, with the same data set, we can estimate the advantage function. For that, we first estimate a value function. Now, the value function V has too many states, right? Too big states. It's essentially infinite for us. Okay, infinite state. So we got to do approximation. Okay, do the regression. Okay, using a function form to approximate function approximation, approximate value function. Okay, to do that, we use a supervised learning. To do supervised learning, we need to know the target value at select points. Okay, target value. This target value at this select point, we use this data to estimate that. Okay, so you can. This v function value function is a. It's also called a path to go or reward to go function, right? Reward to go function. You currently at the t time epoch t, and in this state, and from now t to all the way to the end of the day, what's your expected reward? Okay, and the current policy pi. Okay, so that's this one here. You can estimate that from data. So once you have that, we do solve another optimization problem here. It's a supervised learning problem, and that's get your approximation of the value function. Once you have an approximate value function, you can evaluate this. So this is the way we approximate the advanced function. Okay, so again so we're using value function approximation here, and then get the approximation of the advanced function. All right. So you have advanced function estimation, and you have the empirical optimization objective value, right? So you apply the add-in algorithm, you can get a new policy. Okay, new policy. So that's the PPO algorithm entire cycle. Okay. All right. So this is the. I have two plots here, the numerical example. This one is taken from this paper by in 2019 paper, which was published in Operation Research. And there is the paper is using model, okay, using model. So the model assuming all the parameters known. How do you efficiently do the repositioning, okay? So the performance, the data, the model that suggests the data is actually from released from DD, okay, from DD. This was, I believe, released in 2017 for some level of competition. I think that's really helped the community a lot, okay, that data set. So what you have here, this is the curve here. Let me use different color. Yeah, this one is from that paper, 2009 paper, OR paper. So the matching rate is about 83-ish, okay, the matching rate. So they use the assuming model that all available, all the parameters known. You know when is the rush hour, which pattern, etc. That's this one here. You see the PPO algorithm is do the policy iteration. Remember earlier I talked about policy iteration, right? PPO is when policy, each step is an improvement. And then you can see here the gradually improving and initially improving rapidly and improving eventually is exceeding the performance reported in the OR paper, okay? And there's also another curve here. This one is that suppose we turn off the repositioning option. The platform not allowed, Java is not allowed to do any repositioning. This is and we do the best. We also apply the same reinforcement learning algorithm to optimize. And that's the performance from, so it's below around 70, 73%. Okay, so that's the matching rate. Okay, so significantly low. Okay, and this is for a smaller network. It's you observe similar kind of things. So the PPO reliability is improving over the time. Okay. All right. I don't have time to go into detail about this thing. I just want to see that actually experts on the audience, Professor Zhu, Dr. Qing, and Dr. Ye, Jinping, good colleague, and they are really the pioneer, the leaders working in this area. I think the key difference I want to see, I want to point out that at least seemed to me, reading some of the papers, is these papers is with the driver centric. The optimization is focusing on each driver, what kind of assigned base assignment for them. Okay, be keeping track of. And another thing is that their approach, the deep reinforcement. I'm just put on some deep reinforcement learning related paper, okay, for ride hailing. And this is a value-based. Instead for current, today's talk is focused on policy-based, right? Policy-based, directly optimize the policies. Okay, so that's a major difference. And I think there's a paper here, more recent paper, 2022, 2021, that's a Q learning based, which I yet to digest fully. Okay, so that one is a Q learning something. But I want to emphasize the PPO is a very natural from operational point of view that you can operate. Let me actually move to the slides, next slide, last slides, so that it's a PPO is a policy. It's a policy improvement area. So you can implement current policy in your service system for a number of days, collect episodes, enough episodes, and then you can update, get a new policy, and then stay put for this new policy operating for capital K number of days, and then you do update, get a new policy, these things. And this way we'll make sure your new policy also is not changing much, deviated too much about from the previous policy. So it's not drastically redo everything, right? Once your initial policy is reasonable enough, you can gradually improve, okay? So let me mention a few, maybe one key challenges, okay? Some key challenges, okay? So currently, drivers, they do not always listen to the platforms, right? But they do repositioning themselves, right? They think that a certain area is a good, better, get better assignment, etc. Right? They do that. So at this point, to be actually convincing that our framework is useful, is something has the advantage. I think they need to do a study that more well planned, designed study. So, but for that we need data. Okay, data to understand current driver positioning decision, which we don't have, and this may right. It's impossible to do unless we have some partnership with certain platforms. So with that, I'm going to stop here and turn to the chair of the session.
Thanks
you, Professor
Dai,
I
for your very
think
nice talk. I'm hearing some echo. Okay, yeah, it's fine now. Yeah, thank you, Professor Dai, for the very nice talk. So we'll have some time for a discussion of questions. So first of all, let us see if there's any question from the audience. And please feel free to post the questions in the chat box. Or you can raise your hand by pressing the reactions at the panel at the bottom of the Zoom window. So while we are waiting for the audience to raise questions, I have several questions here for Professor Dai. So the first question is that, so the sequential decision making process that you present here really provides a way to scale up the training of a system level policy, which has to make really non-trivial planning within the batch at regular intervals for multiple agents, and which otherwise are basically suffer from the dimensionality problem. At the same time, I think an artifact, a potential artifact that's brought by such serialization of the decisions is the implicit sequence on the decision that you impose on them. So I was just wondering, but here, the actions are actually sampled from the policy function, right? And it seems to me that you can arbitrarily just skip a action by not executing it, and thus keeping the state intact, and then you can sample again, resample, and get the next action. So the order, the output order of the action seems to be, you can put it in any order. So I was just wondering, is there any impact on the performance according to the order of the action that's output from the policy function? Do you have any insight on that?
Okay, I think you really, Tony, you're really hitting on the nail, this thing, right? So basically, what you're saying, by treating using this so-called atomic action approach, you likely, there's very good chance it's a sub-optimized, right? You are doing, you are not taking global view, right? Something just taking one trip at a time. And when you do the first assignment one trip, and you ignore, could be there maybe another trip maybe much better, or something that much better. So right, this is right. This is the key step to achieve scalability. Okay, and I have to say that something. This one is I'm certainly amazed. I'm very happy that this thing is working. Okay, it's working. Now I have to also report there's another setting. We also achieved observed similar things. Okay, can beat the state-of-art results. And at this point, I'm hopeful. This is the thing is somehow the policy network. Okay, policy network, neural network is learning that. Picking that. Okay, reinforcement learning is learning that. You think that at this point, this assignment may be marked, but somehow but first of all, you do the assignment, mark the assignment, you also change the state, right? We need to change the state, okay? After do the mark one atomic action, we need to change the state. And if they got a new state, then you, the policy will get to, allow you to make a new distribution of select OD pair to the. So yes, while on surface is this may be suboptimal, but in first of all, two things on practice that we have observed good empirical performance, and not just for this problem, for other problems as well. And the second of all is that I think, come to think about why is that the neural network somehow smartly is able to anticipating all your future other decisions. If there's a suboptimal future decision, next step is somehow the neural network in the training process try to correct that.
Okay. Yeah.
But that's really the heart of the matter. I think that's no theory here to guarantee that. Yeah.
See, yeah, and you mentioned other application. Yeah, I was actually was about to ask that. It seems that like this approach is general, not necessarily just specifically for ride-hailing reposition problem, but potentially in general for any any batch decision problems or batch dispatching problem that could arise in industry, for example, the some job scheduling problem and so on. So do you see that?
Tony, you need to say again. Your voice is trade off.
Sorry.
I didn't hear a complete sentence. Can you repeat that? It's somehow your voice is trained.
Oh, okay. Yeah. So I was just wondering, do you see this as a general pathway for solution to solve, general batch dispatching problems? Because it seems that this framework is probably not just specifically for ride-hailing or reposition problem, but it can potentially apply to any.
Absolutely, Tony. The answer is absolutely yes. That's my hope, at least. And I think this the contribution of this paper. Of course, one side is demonstrating that it's relevant to the model framework or something relevant to ride-hailing. But to be honest, I think that the methodology contribution here is this one, atomic action things. And I do believe that for batch operation, as what you said, that this is I think potentially. I absolutely agree with you that indeed this our hope. This will become a viable methodology to that. Somehow the sequential decision, because of the reinforcement learning setting, batch decision, reinforcement learning, during the training, you can go back again and again, right, training, so that it's try to correct some myopic, the bad decision early steps somehow can be corrected. So thank you. I think the simple answer is yes. I hope so.
Cool. Yeah, there's a question from the audience. So the question is, from the experiments that you showed, the percentage of fulfilled requests is gradually increasing. Does it mean that at the beginning we cannot give good match? Will it disappoint passengers at the beginning?
Okay. First of all, this is doing two things. Okay. Yes, I think earlier the algorithm does not give a good match, and this is because we started with a random matching policy. Okay, random matching policy. So if we really want to be to work with a platform or something, we probably want supervised learning with the current policy, right? We want to do supervised learning with the current policy starting from that. That you already from there maybe you start with the 70% match rate already something. Second of all, I mean it's for the whichever one is asking the question that's something that this is at algorithm level, right? We're doing this in the lab, okay, doing this thing. The real deployment is going to deploy at toward the end of after maybe 200 round of policy iteration training. Then we at least a few round of policy iteration. Then we deploy that. I mentioned in the talk as for practical purpose, maybe you start with something already good policy, okay, good policy. You collect sample for K days. Then you do one policy improvement, maybe just even that you can get 1%, 2% improvement of matching rate. And you start from that one. So you don't need to do 200 iterations. No, you just need to one iteration to improve to the previous policy.
Yeah, thanks. And I guess my one last question is on the practical side. So in the update of the policy, when you are doing the supervised learning to approximate the value function, there's a parameter K, which is number of episodes that you simulate at each policy iteration. Is there any guideline in terms of how large K should be to determine how well the approximation to the value function is?
Yes. How many episodes needed? I mean, that's a tough one. That's need to be right. This is a hyperparameter, and we have not experimented in detail, say how sensitive to this one is. Okay, but I think in terms of theory, I think it's going to be very difficult to determine because right. So the in terms of theory side, of course, the larger the better, right? But I think I think we have done k equal to 30. We have done k equal to 300. Both, okay, did something. So it's I would say in practice, I'm hoping that within 1 month, 30 days, maybe enough. Okay, something. Okay, 30 days, 30-day episode can get meaningful improvement. That's a, okay. That's a very right. I don't have a good answer to that. Yeah.
Okay. Yeah. Actually, there's another question from the audience in the chat box. What kind of reasons inspire you to decide to use PPO? Was it just a trial based on its former good performance, or is there any other reason like PPO is shown to be suitable to this kind of problem?
That's an excellent question. Okay, I think this is all because the PhD thesis work of Mark Grossman, and he did the last few years. We have been working on control in the constrained environment, or specifically on the Q network. The control with the constrained resources, right? So these things certainly doesn't show up in the game setting like in AlphaGo Zero or these things, right? But in a data center operation or this ride hailing, these things, the resource is a constraint. So in this setting that we first did Q learning, we saw something, we tried many different ways. And eventually for the Q network setting, we found the PPO with deep neural network can get us easily, can get us the best performance. Well, not easily, I would say the better word is robust. So easy, less that tuning, and a lot of things can be automated. So in Mark's, by the way, he received this finalist based paper with the Applied Public Society of Informs, and that paper is really demonstrated PPO can be good way to do that. Okay, to achieve to be the again, I would say robustly easily, right? Not much extensive tuning. So that's the thing. That's why you want to use PPO on this problem. By the way, we did the first also all of them. Before that, we tried maybe a year, almost 2 years. Try to come up a good engineered feature function, value function approximation technique. We couldn't beat the state-of-art performance. So it's a lot of painful experiences, okay? And eventually lead us to this PPO, this is a robust one. And but I mean, that question is impossible to answer completely, right? Maybe we didn't do good enough job on Q learning. Maybe we didn't do something, right? So it cannot be exhaustive, but I just tell you experiences that the first that our team, some of these maybe many months, even years, a struggle. Okay, try to find a good algorithm. Okay, so I hope this answer. Now, in addition to that, I think PPO is it's a policy improvement algorithm. as I said, for many service operation systems, it's very natural. You observe data, number of days, you do improvement. And do improvement in the sense that here you don't have to do big improvement, it's small improvement. And I think this is something very easy to share to the upper level management, that something your policy, new policy is not drastic improvement, not drastically different from the previous policy. So this is a feature.
Yeah, I think intuitively that also makes sense for a lot of practical problems that you want to make somewhat conservative steps in terms of the policy updates. Cool. I think we answered all the questions from the audience, and I think it's also about time to close the session. So let's thank Professor Dai again for the excellent talk that he brought to the Applied Reinforcement Learning Seminar. And I really hope to meet you offline in the near future when we have a chance. Yeah, and
all right, well, I mean, next time if I go to Bay Area, I will come to visit you. And thank you for you and also Hongtu for giving me this opportunity to share our work. Thank you.
Yeah, thank you very much, and thank everyone in the audience for coming today and attending the talk. And we'll see you next time. Thank you.
Bye-bye.
Yeah, thank you. Bye-bye.